We have an urn here in number 8 that contains 4 red, 3 yellow. Let's draw that so we can summarize what's going on here. So here's our urn. There's 4 red and 3 yellow. So altogether we've got 7 balls in there. And what we're going to do is this. We're going to choose a ball at random from the urn and then replace it. And then we're going to choose a second ball from the urn but not replace it. And then we're going to choose a third ball from the urn. What's the probability that the first 2 are red and that the third is yellow? I'm seeing it like this. We're going to have a first draw, then a second draw, and then a third draw. And what we want here is this. What's the probability that the first 2 are red and the third is yellow? So what I want here is I want a red ball here, a red ball here, and then a yellow ball here. Let's see how we can do that. So out of the first, in the first draw, out of this urn, we're going to choose a red. Now there's 7 balls altogether, so the probability of getting a red is going to be 4 out of 7. So how about 4/7 right there? And then what we do is this. We replace that ball, right? So we draw a ball, and then we replace it. So there's still 7 balls in here. And then what we want is a red one here again. So there's still 4 red, and then 7 balls still. Times. And now what we're going to do is we don't replace that ball, right? We take 1 out of this one, but we don't replace it. So there's only 6 balls left, and we want a yellow. There's 3 yellows out of those 6. So there's 3 yellows out of 6. So we're going to multiply these together. So we're going to get 4 times 4 times 3 over 7 times 7 times 6 equals, and that's equal to 4 times 4, 16 times 3 is 48. And this 7 times 7 times 6, 7 times 7 times 6, I don't know what that is. That's 294. 294. So let's convert it to a decimal. So if we convert that to a decimal, we're going to get 48 divided by 294. And I'm getting 0.1633 if I round it off. 0.1633 when I round that off. So what that tells us, if we were to do this experiment over and over and over and over again, that about 16% of the time, right, about 16% of the time, we're going to get this event, red, red, yellow. Now, in 9, we have a mother and a father, and there are 3 kids, and they're randomly standing in a row for a photograph. What's the probability that the father will be standing to the right of the mother? So let's see how this can happen. We've got our 5 people here, and what we want is the father to the right of the mother. So where could the mother be so that the father's to the right here? So the way I'm looking at this is that the mother could be here, right? The mother could be here, and let's see. So then we would have, if the mother was there, we would have 4 choices for the father, right? We would have, the father could be here, 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 or here if the mother was here. Or the mother could be 1, 2, 3, 4, 5. The mother could be here, in which case the father could be in any one of these places. So there's 3 choices for the father. Now 1, 2, 3, 4, 5. The mother could be here, in which case there's now 2 choices for the father. Let's see if I can get that to right. 2 choices for the father. Or 1, 2, 3, 4, 5. The mother could be here, and in this case there's only 1 choice for the father. So there's 1 choice for the father. So what I'm counting here is that there's 1, 2, 3, 4 different ways that the father could be to the right of the mother. So just to make that decision, there's 4 ways that could happen. So we're going to have a 4 times, and now how many ways can we arrange the other 4 people? Well, there's 4 people, and that's going to be 4, 3, 2, 1. That's going to be 4 factorial. Right? Does this make sense here so far? We've got 1, 2, 3, 4 ways that the father can be to the right of the mother, And then we've got the other 4 people in the family. So just suppose we had this position here, the father. Well, where could it be? There's 4 people. So the father maybe and the 3 kids, or, there's 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. There's 4 factorial ways to arrange the other family members. But now this is a probability. So we have a fraction here. So the bottom number is the number of ways in the samples, number of elements in the sample space. That is the number of ways that we can arrange 5 people. So 5 people can be arranged in any one of 5 factorial arrays, right? 1, 2, 3, 4, 5. That's the total number of ways that can happen. And when I made that computation, I got 0.8. Right, what's going to happen here is you can do this in your head. Probably this is going to be that 4 factorial will cancel with 4 factorial from there, leaving just the 5, and then you get 4 over 5, which is 0.8. Now, in number 10, we've got a multiple choice exam with 5 questions. As soon as I see that, I'm looking at this. 1, 2, 3, 4, 5. There's our 5 questions, and each with 4 possible answers. Right, so we can answer this like maybe A, B, C, D, A, B, C, D, and so on. Now, assuming all the questions are independent of each other, what's the probability that a person who takes a quiz and guesses at all the answers gets the first 4 right and the last one wrong? So what we want here is this. We want a right, a right, a right, and a right, right? The first 4 have to be right, and the last one has to be wrong. So what's the probability now of getting the first one right? Well, there's 4 parts, and if you just guess, that's probably going to be a 1/4, right? 1 out of 4 chance of getting that one right, a 1 out of 4 chance of getting that one right, a 1 out of 4 chance of getting the third one right, a 1 out of 4 chance of getting the 4th one right. But now what we want is the last one to be wrong. Well, there's 3 incorrect answers out of 4. Let's make that multiplication. So my calculator is showing that this comes out to be 3 over 1024. And if I convert that to a decimal, I'm getting 0.0029 when I round it off to 4 places.